Let us continue our study of absolute and conditional convergence. Definition. Let summation an be a series, a rearrangement of summation an is a series of the form summation a sigma n, where sigma from natural numbers to itself is a bijection. So this is capturing in a very rigorous way what it means to permute the elements of a series or rearrange the elements of a series. In the last module, we saw that if you rearrange the terms of a conditionally convergent series, all sorts of weird things can happen. So we have not formally defined what a rearrangement is in the last module, and now we have rectified that issue. Now what I am going to do is I am going to prove that this pathology, that when you rearrange a series you get a different series, cannot happen when you consider absolutely convergent series. More precisely, making this precise, theorem: if sigma an is absolutely convergent, then all rearrangements converge to the same limit. So when you rearrange a series that is absolutely convergent, you cannot get a different limit. Proof. First, I am going to show that a rearranged series will converge, in fact will converge absolutely. So let sigma from n to n be a bijection. Let Tm be the sequence of partial sums of summation mod a sigma n. I look at the rearranged series with absolute values, of course, and look at the partial sums. Let Sm be the sequence of partial sums of summation an modulus of the original series. Okay, we have to now show that Tm in fact is convergent, but Tm is an increasing sequence, right? Simply because at each stage you're just going to add a non-negative term to it, and Sm is bounded above. Sm is bounded above by, let's say, k, some quantity k. Why is Sm bounded above? Because summation mod an converges absolutely. Convergent sequences are bounded, therefore Sm will have to be bounded. Now what we do is the following. Let L be equal to maximum of sigma inverse 1 ... sigma inverse m. What I am doing is I am looking at where the first m terms of the rearranged series are coming from in the original series. Okay, now it is clear that SL is greater than or equal to Tm. Why is that the case? Well, look at what I have done. L is the maximum of sigma inverse 1 to sigma inverse m. That means every single term that comprises Tm will occur in this sum SL also, and possibly more terms can occur. Therefore, SL will have to be greater than or equal to Tm. This shows Tm is bounded by K, and by monotone convergence theorem, Tm is convergent. This shows that summation A sigma n converges absolutely. Now, this doesn't finish the proof. We still have to show that this converges to the same thing as summation an. Now we reuse notation and let Sm denote partial sums of summation an and Tm that of summation A sigma n. Now we want to show that Tm converges to the same limit as Sm, and we can achieve that by showing that mod Sm minus Tm is converges to 0. If we can show this, we are actually done, right? Now, how are we going to show that mod Sm minus Tm converges to 0? We pull the same trick that we pulled last time. Observe that for sufficiently large n, we have summation mod Aj, j running from n to infinity is less than epsilon. Okay, is less than epsilon. Okay, so I have to fix epsilon greater than 0. Given any epsilon, for suitably large n, we can find the series summation j equal to n to infinity mod Aj will be less than infinity. This is just rephrasing the fact that the series of absolute values must converge, because that is there in the hypothesis. Now, what you do is you look at this mod Sm minus Tm, then for suitably large m, m, the terms mod Aj, j less than or equal to, or less than n itself is enough, less than n will occur in Tm. Not mod Aj, just Aj. The terms Aj for j less than n will occur in Tm. How do we know this? Well, we can just use the same trick that we used here. The exact same trick that we used here will give us this. Okay. Now this sum will comprise only of those terms Aj with j greater than or equal to n, right? Because the first n terms will get cancelled. So what happens is we get summation, what we get is mod Sm minus Tm is less than or equal to summation j equals n to infinity mod Aj for j suitably large. Not for j suitably large, for m suitably large. Okay, and this we have already made less than epsilon. This we have already made less than epsilon. So here is the brief argument what has happened. We want to show that mod Sm minus Tm converges to 0. We choose small n so large that we have this, that summation j equal to n to infinity mod aj less than epsilon. Then we ensure that the modulus of Sm minus Tm, the first n minus 1 terms get cancelled. This we do by the same trick that we did for the absolute values. So what you will be left with is just those terms, summation j equal to n to infinity mod aj, and that will be less than epsilon. That will be less than epsilon for m suitably large. Okay, so this concludes the proof. This concludes the proof. Okay, so please go through this proof again. I am intentionally leaving a number of steps under the carpet for you to fetch. Now we come to one of the celebrated results which I find utterly fascinating. It's called Riemann's rearrangement theorem. Rearrangement theorem. Suppose summation an is conditionally convergent. That means it converges but not absolutely. That is, you are not just given that it might or might not converge absolutely. You are given that it does not converge absolutely. Conditionally convergent. Then given any L in R, we can find a rearrangement such that summation a sigma n converges to L. How's that? No matter what real number you choose, I can rearrange this conditionally convergent series and make it converge to L. Now this result is a bit technical, and this is going to be one of the first really long exercises in this course. I'm going to leave you with a number of steps on how to prove this, and you're going to fill up the details. Okay, so let's see how this goes. Step 1. Show that there are infinitely many positive as well as negative terms in an. It cannot happen that an has only finitely many positive terms. It cannot happen that an has only finitely many negative terms. This is a very easy. This is just a warm up. We will actually, step 2 will be something even stronger, and that is what will be required. But I think it's a good idea to start with a warm up to get a sense of what is going on. Okay. Note, for step 1, you have to use the fact that the series does not converge absolutely. That means you will be showing that if there are only finitely many positive terms, then the series actually converges absolutely. Step 2, define Pn to be equal to an if an is greater than 0 and is equal to 0 if an is less than or equal to 0. Okay, I'm defining a new sequence Pn. P stands for positive here, whose value will be an if an greater than 0, and whose value will be 0 if an is less than or equal to 0. Okay, so next I define a negative. I don't want to use nn, so maybe I will just use Rn. Rn will be an if an is less than 0, and this will be 0 if an is greater than or equal to 0. Okay, so Rn is collecting together all the negative terms of the series. So Pn collects together all the positive terms, Rn collects together all the negative terms. Okay. Step 2 is show that if you don't mind, I will put a minus sign here. I will put a minus sign here because it will make the statement I am about to write simpler. Show that both Pn, or rather summation Pn and summation Rn diverge. Okay. Both summation Pn and summation Rn diverge. In fact, they diverge to infinity, plus infinity. So what this says is that if you sum up all the positive terms and if you sum up the negative of all the negative terms, both diverge to plus infinity. Okay, this is step 2. Again, you have to use the fact that the series An does not converge absolutely to show this. Step 3. Given L, given the real number L, given the number L, what you do is collect together the positive terms in An, collect together the first few positive terms in An such that the sum just exceeds L. Okay, so this step might require a bit of elaboration since I'm expecting you to fill up the details. This is the following. You have A1 plus A2 plus A3 plus so on. Some of these terms are positive, some of these terms are negative. What I'm doing is I'm collecting together all the positive terms. Say A1 is positive, then I put it here. Then I'm putting A3. Let's assume that A2 is negative. Let's assume that A4 is positive. I am collecting together the first few positive terms. Because summation Pn diverges to infinity, there will come a point that, let's say A27, such that A27 just exceeds L. That means if I sum up the first 26 terms, I should not exceed L. But the moment I sum up the first 27 positive terms, sorry, I made a mistake. There may not be 27 of them because some of them will be negative. So let me rephrase the last statement. What I want to say is if I sum up the first positive terms coming from A1 to A26, it should be less than R. But if I sum up the positive terms coming from A1 to A27, that should exceed L. Okay. So you are going to keep adding the positive terms till you just cross L. Okay. Do this. So this is going to be the first few terms of our new modified series such that it first exceeds L. Now what you do is the following. You start clubbing together the negative terms. So in particular A2 is a negative term because it's not appearing in the previous thing. You start summing up the negative terms. Let's say A5, A7, so on. Let's say till A37. I'm plucking numbers out of the air. Don't fuss too much on why I'm choosing these particular numbers. So A1, A2, A5, A7, I'm adding all the negative numbers. Note that this series Rn also diverges to plus infinity. So in particular, this quantity can be made as negative as you desire, right? So what will happen is when you add enough of these terms to the previous set of terms, there will come a point where it will become less than L again, right? Where that when you sum up the first few positive terms and the first few negative terms, it will become negative again. Go all the way till it just crosses L, but from the other side. Okay. So intuitively the picture is L is here. You first landed here, then you're slowly decreasing by adding terms, and then just when you cross L again, you stop. Okay. So now what you do is the following. You keep adding positive terms again. Let's say A29, A31, ... till A43. Again, I'm plucking numbers out of the air. And what should happen now? Well, it should start increasing because I'm adding positive numbers till it just crosses over L again. Till it just crosses over L again. Now repeat this process. Repeat this process. Repeat this process. Keep adding positive terms till you just cross L, then keep adding negative terms till you just cross L again from the other side. Then you're just ping-ponging between the left side of L and the right side of L. Okay? Repeat this process till the series is exhausted. That means, I mean, technically you cannot do it because it's an infinite series, but this can be made precise. Repeat this process till the series is exhausted. So you have found a rearrangement. You have found a rearrangement. So step 4 is to show that this rearranged series converges to capital L. Fine. So this will not be hard because at each stage you notice that it jumps left and right between L, and the magnitude of the jump will become smaller and smaller because the original series converges. Therefore, the nth term of the original series must converge to 0. I'm essentially handing you the proof in a silver platter for the final step, but there's still all the details for you to fill. So I urge you, please fill up the details, finish the proof entirely on your own. So this concludes this module. You're watching a course on real analysis.